Hello everyone, here is Khaled Omar, and in this video I'm going to demonstrate the first chapter of the CCNA 200-301 Volume 1, which is Introduction to TCP Ib Networking. So this is the first video that I'm going to demonstrate in the CCNA series, new certificates from Cisco, and coming videos will demonstrate other chapters, but in this one I'm going to demonstrate chapter 1, which is related to Introduction to TCP Ib Networking. So let's start. In the beginning, I would like to give a simple example that demonstrate how computer networking started by giving a simple example that shows you how the idea came from. So let's assume that we have someone here called Muhammad from Egypt, and Muhammad would like to send a mail to Jasmine. So he will send a letter. By the way, he is sending a mail, not an email. He is sending a letter inside an envelope to Jasmine in Germany. So the process that the letter will take, since Muhammad will write the letter until received by Jasmine, will give you a good example on how networking works. The main idea of the computer networking came from something like that. So let's think that Muhammad would like to send a letter to Jasmine. So what he needs, first of all, he needs a pen and paper, ink, envelope, and using these three things, he will be able to write a letter and inserting the letter inside the envelope. And then what? He will insert the letter inside the envelope and write the destination name, or the destination person that he would like to receive that letter is Jasmine, and she is located in Germany. Once he do this process, he will insert that envelope in the post office box, and then the post office man will come and take the envelope and take the envelope to the post office inside Egypt. And then once the post office receives the letter, it will start do some processing based on the destination address written over the envelope. So the post office will decide that the letter should be traveled to Germany, and once the envelope is delivered successfully to Germany, another post office man will take the envelope and deliver it to Jasmine. You see how this process accomplished? It started by a pen and paper, ink, envelope. This is something like the application. The pen and paper and the ink and the envelope are considered the application that Muhammad used to send a mail to Jasmine. Let's give another example that will simplify the concept of networking. Let's assume that Muhammad from Egypt, he would like to send mails to Jasmine, David, and Zabina. And by the way, David is Jasmine's father and Zabina is Jasmine's mother. So they are located in the same house, in the same building, in the same flat. So Muhammad will bring a pen and paper and write a letter to Jasmine, then write a letter to David, her father, and then write a third letter to Zabina, Jasmine's mother, and send the letter through the post office to Germany, where Jasmine's family are located. And each one of them will receive the appropriate letter based on the name written over the paper or the letter. See, this is give you an example how the communication process is accomplished, how there is no confusion or conflicts or something like a mistake in the letters. Jasmine will take her letter based on the name on the letter or the paper. David will do the same, receiving the correct letter because of Muhammad wrote his name over the letter, so he received the second letter. And the same as Jasmine and David, Zabina will receive the third letter because she has her name written over the letter. So this gives you a simple example how the networking concept came from. So let's discuss how computer networking works. Let's assume that we have Bob with his laptop connected to the internet, and he would like to communicate with Larry, which is located in USA, and Bob in UK, through the internet. This is the main idea how networking works. First of all, there is something called a networking model, and there are multiple networking models. Each one is developed by a specific vendor. But to define a networking model, let's say that it is a structure and different categories or layers of standards and protocols. So the networking model, let me use the pen. The networking model is a structure and different categories or layers of standards and protocols. So networks works correctly because the various devices and software follow the rules of the networking model. That's why when you have a PC or laptop and you are trying to communicate with someone else in a different location, the communication process is accomplished successfully because each device follows the rules that the networking models use through standards and protocols. Those rules come in the form of standards and protocols, which are agreements of a particular part of how a network should work. The world of networking has used several networking models over time, and each one is developed by a specific vendor. So, as new standards and protocols emerge over time, networkers can think of those new details in the context of a networking model. So, a networking model collects all the standards and protocol that will be used in the communication process inside the network. That networking model defines rules about how each part of the network should work, as well as how the parts should work together so the entire network functions correctly. So, let's start by the first networking model, not the first one that was introduced, but the most recent used one, because this is the only one that we are using, all of us are using it right now. So today, TCP Ib is the most pervasive networking model in use. Each device supports TCP IP. Every computer, operating system, every mobile phone, and all other devices. Like, for example, every network built using Cisco products, using Cisco switches, routers, firewalls, IP phones, etc. And by the way, we will focus here only about Cisco products because we are demonstrating CCNA 200-301, Volume 1. And it is related to Cisco products and Cisco certificates. So all these devices today supports TCP/IP. So let's discuss a little bit about the history that led to TCP/IP. First of all, as we mentioned in the previous slide, today the world of computer networking uses one networking model, which is TCP/IP, and we will define what is TCP and what is IP, and from where this name came from. So another model was introduced by IBM, and they called it Systems Network Architecture, or SNA, and it was introduced in 1974, before TCP/IP actually. And other vendors also created their own proprietary networking models. So we had multiple networking models, each come from a different vendor. The first one was, I think, the Systems Network Architecture came from or published by IBM, and then other vendors created their own networking models, and each one gave it a name, and there was something like a battle, because eventually only one should be used, so all connected hosts will be able to communicate to each other through standards and protocols. And as you can see here, IBM with its SNA, there was also another networking model called DEC, and other vendors also created their networking models. So in the late 1980s, more than 3 networking models existed. In 1990s, TCP/IP started to be presented, and it came in the scene. And there were also IBM SNA and DEC, another networking model, and TCP/IP. But eventually, in 2000s, the beginning of 2000s, TCP/IP became the only acceptable networking model, or the official networking model for all network connected hosts. And recently, all of us are using TCP/IP. If you have a laptop, if you have a PC, if you have a mobile phone, all of them supports TCP/IP networking model. So another model was introduced, but that model had a noble goal. What was that goal? That goal was to standardize data networking protocols to allow communication among all computers across the entire planet. But there are also still competing networking models, such as TCP/IP. That's why by the end of the 1990s, TCP/IP had become the most common choice, and OSI fell away. So there was something like a battle between TCP/IP and OSI. That's why we call the OSI networking model the OSI reference model, because we will use it in the demonstration purposes, and you will find it in multiple books. So let's give an overview of the TCP/IP networking model, because this is the conclusion that after the history is that all of us, all computers connected to networks, supports TCP/IP. So let's give an overview of the TCP/IP networking model. Let's start by saying that the TCP/IP model both defines and references a large collection of protocols that allow computers to communicate. So TCP/IP defines a large connection of protocols. Each works on a specific layer, and we will demonstrate later what are those layers and what each layer do. So to define a protocol that works with TCP/IP, TCP uses documents called requests for comments or RFCs. And these RFCs are issued by the standardization organization that works for issuing internet standards, which is called IETF, Internet Engineering Task Force. This is the organization that is responsible for issuing the request for comments, and each request for comment or each RFC define a specific protocol or a group of protocols that works together for a specific function. And the IETF has also some other organizations inside it that works together to make internet standards. And you can find these RFCs using any online search engine such as Google. You can Google RFC and write a number, and it will give you all the details of that RFC that describes a specific protocol or a group of protocols that aim to do a specific function. There is also another organization that is specialized in a specific layer of the TCP Ib, and this organization is called the Institute of Electrical and Electronic Engineers, or IEEE. IEEE defines Ethernet LANs, and this Ethernet LANs works on a specific layer at the TCP Ib. So the TCP Ib model does not define Ethernet in RFCs because Ethernet LANs are issued by IEEE, so there are no RFCs with the IEEE, but refers to IEEE Ethernet as an option. So some layers has RFCs and some layers have protocols such as Ethernet LANs that is issued by the IEEE. So we have two organizations that are responsible for issuing internet standards or network standards. So as an overview of the TCP Ib, to help people understand a networking model, each model breaks the functions into a small number of categories called layers to make it easy to understand, number one, and to make it organized for each host connected to the internet to follow the layers. And this layer, each layer, includes protocols and standards that relate to that category of functions. As you saw with the example of sending a mail from Muhammad to Jasmine, this process that required a pen and paper, ink, envelope, this works as the application layer at the TCP Ib model. This is the application that you are going to do, whether you are going to browse a website, send a mail, download file, remote access for a specific device. All those are considered as an application, and we will discuss each layer of them in this video, but not in details, because each one will have a specific chapter for discussing the complete function of each layer. As you can see, TCP Ib model consists of 5 layers: application, transport, network, data link, and physical. And they are numbered from down to up. Layer 1 is the physical, layer 2 is the data link, layer 3 is the network layer, layer 4 is the transport layer, and layer 5 is the application layer. Keep in mind the example that we gave in the beginning of this video, where Muhammad tried to send a mail to Jasmine, and then Muhammad tried to send 3 mails to Jasmine's family. The tools that he used are the application. The post office will do the function of the transport layer and the network layer. Specifically, the transport layer, when Muhammad tried to send 3 mails, transport layer will deliver each mail to the correct person. The network layer works as the post office that will use the address Muhammad wrote on the envelope and deliver it to Jasmine's location. The data link will determine the data link and the physical layers will determine the medium that the post office used to deliver the mail from Egypt to Germany, from Muhammad's house to Jasmine's house. So, let's give some examples of protocols that each layer use. As you saw that the TCP/IP uses 5 layers, the application layer, let's give a specific example about it. What is the application that you are going to do on your computer? If you are going to browse a website, you will use HTTP. If you are going to send a mail, you will use SMTP. If you are going, by the way, an email, if you are going to send an email, you will use SMTP. If you are going to retrieve the email from the mail server, you will use POP3. If you are going to do, for example, download file, you will use FTP. And FTP is used for downloading or uploading files. If you are going to do some remote access for a specific device, you will use a network protocol called Telnet. Or you can use secure shell. Those are some examples of the application layer protocols. There are many other protocols, and you can search for them as we will give some examples about some of them. So for the transport layer, actually there is only 2 protocols, TCP and UDP. And by the way, let's give the names of each one of these protocols. HTTP stands for Hypertext Transfer Protocol. POP3 stands for Post Office Protocol, version 3. SMTP, Simple Mail Transfer Protocol. FTP, File Transfer Protocol. And Telnet is Telnet for remote access, and SSH for secure shell. TCP stands for Transmission Control Protocol. UDP, User Datagram Protocol. So for the application, we give some example protocols, and for the transport layer, we give the only 2 used protocols, TCP/IP. And by the way, because TCP is considered one of the most important protocols that the TCP/IP uses, the name came from this protocol. Then for the layer 3, the internet or the network layer, it uses mainly the IP protocol or internet protocol. And there is another protocol that is used with the IP called ICMP, but mainly the most important protocol in this layer is IP, and hence the name came from. TCP/IP, the most important protocol that works at the transport layer, and IP, the most important protocol that works at the internetwork layer. Then let's give an example protocol of the data link and the physical layers. We have wired Ethernet and wireless standard, which is 802.11. This is for wired LAN, the standard for the wired LAN, and IEEE 802.11, the standard for the wireless LAN. So those are some example protocols of the TCP/IP networking model. Let's take each layer and give it some demonstration about it. We will not deep dive inside each layer because each layer has a specific chapter, but we will give some examples on how each layer works inside the TCP IP. And in this slide, we will start by the TCP IP application layer or layer 5. Actually, the application layer does not define the application itself, but it defines services that applications need. So it defines services such as browsing a website, sending an email, retrieving an email, downloading or uploading files, and so on, as we mentioned in the example protocols. So we will take one of this example protocol, and we will give an example here about it. The application protocol HTTP defines how web browsers can pull the contents of a web page from a web server. Let's assume that we have here a PC or a laptop that has a web browser and Bob using it, and this computer is trying to browse the contents of a website or of a web server called Larry. So as a first step, Bob will send a message to server Larry requesting the content of the web page. So it says, give me your web page. Once the message will be delivered to Larry web server, it will respond back in step 2 with the homepage file, which is called home.htm. This is how browsing a website works. The browser sends a request, a get, to get the website, and the server responds with a reply and the data of the web server. So in short, the application layer provides an interface between a software running on a computer and the network itself. As we saw, the web browser as a software which runs on a computer, and the application layer works as the interface between this web browser and the network itself. So in this slide, we will demonstrate a little bit about the HTTP protocol mechanism. Actually, HTTP didn't exist until Tim Berners-Lee created the first web browser and web server in the early 1990s. So this engineer developed the idea of having a web browser and the idea of having a web server, and a web browser do a request to get the contents of this web server. So as a first step, Bob PC or web browser specifically will send a GET request to the web server, and this content are existing on an header. So what is a header, or in this example HTTP header? Header is a place to put information used by a protocol. Each protocol will have some information. This information will be stored inside something called a header, and it is called a header because it is existing before the data. So as you can, sometimes, yes, it exists before the data. So once Bob will send the request from the web browser to the web server, and once the request is received by the web server Larry, the web server will start in step 2 to respond back with a message containing OK in its HTTP header, and the data is sent in steps, or not in one part, in parts. The data will be sent in parts because maybe the file is big, so it will be segmented and sent to POP. And steps 3 and 4 can be still the data, more information about the data. So for HTTP protocol mechanism, we have something called HTTP GET request sent from the browser to the web server. And we have another message called HTTP reply that has OK in its HTTP header. And then one data only message will be sent from the web server to the web browser, and then the web browser can have all the contents of the web server shown in the web browser. As we saw, to get the web page from Larry at step 1, Bob sends a message with an HTTP header that includes the get word to get the file, and it is stored in the HTTP header. And as we defined, HTTP is a place of information that's used by a specific protocol. The request typically contains the name of the file that is requested by the web browser. It's either home.htm, in this case, it is requesting the home page, or if no file name is mentioned, the web server assumes that Bob wants the default web page. And for step 2 in the figure, it shows the response from the web server Larry, this one. The message begins with an HTTP header with a return code 200, because each response have a code. Code 200 means that something as simple as OK returned in the header. It means if you want this the home page, OK, you can have it. HTTP also defines other returning codes so that the server can tell the browser whether the request worked or does not, such as 404. It means web page is not available. As you can see here, if you ever logged for a web page that was not found and then received an HTTP 404, it means not found error. You received an HTTP return code of 404, it means that the web page is not available or not found. At step 3 in the figure, it shows another message from the web server Larry to web browser Bob, but this time without an HTTP header, this part. Why? Because it is the data. The web server will start to transfer the data, and there is no need to more HTTP headers. Headers became before sending the data. This is the request, this is the reply, and then the data. So HTTP transfers the data by sending multiple messages in case of the file is large, each with a part of the file. This is how HTTP works. Hypertext Transfer Protocol. And this is a more detailed protocols that I think we mentioned in one of the slides before, but here is another protocol, example protocol of the application layer that we didn't mention, which is called DNS. And this protocol is used for name resolution. Actually, there are many protocols that exist at the application layer. You can search for any application you are trying to do and find the appropriate protocol. So as we mentioned, web uses HTTP, or for added security, we use HTTPS. If you are going to download or upload file, you use file transfer protocol. If you are going to send or retrieve an email, you use SMTP or POP3 respectively. And IMAP is another protocol that is used for retrieving mails as well as POP3, but uses a different mechanism. For remote access, we use either Telnet without added security or secure shell with encryption to secure the data. You can search for any other protocol using any online search engine that works at the application layer of the TCP Ib networking model. So let's go to the lower layer that has the transport layer in the TCP Ib. The TCP Ib transport layer includes a smaller number of protocols. As we mentioned, the two most commonly used transport layer protocols are the transmission control protocol and the user datagram protocol. There are no more than these two protocols inside the transport layer. So the transport layer protocols provide services to the application layer protocols. Actually, each layer inside the TCP Ib provides some services to the layer above it, which means that the network layer provides services for the transport layer. The transport layer provides services to the application layer. So each layer provides services to the above layer. So transport layer protocols provide services to the application layer protocols that reside one layer higher in the TCP Ib model. And as an example of these services that the transport layer provides to the application layer, we will discuss the TCP error recovery service. Let's go back to the original example when Bob tried to browse a website, a web server Larry. So in this slide, as we mentioned, each layer provides a service to the layer above it. Like for example, the error recovery service provided to the application layer protocols using or by TCP. In this example, as we mentioned before, Bob sent a GET request to get the home page of the web server Larry, and then Larry replied with OK. And in the third steps, it started to send the data and in parts. So let's say that the part 1 of the data has a sequence 1 in the TCP header with OK in the HTTP header, because this is the first part of the website, and then part 2 without an HTTP header but with TCP sequence equal to sequence number 2, and the third part has sequence number 3. Let's imagine that sequence 2 has lost in the network between Bob and Larry. What will happen? The website will have some missing contents. This is one of the services that TCP provides to the application layer. If a number is missing, Bob computer using the TCP network layer will send a request saying, please provide me with data with sequence number 2. And then the server will respond back with the part that has sequence number 2. So TCP provides error recovery service for the application layer. And actually this figure demonstrates in more details the concept of adjacent layer and same layer interaction. How that happens or how that works. The following figure demonstrates a function called adjacent layer interaction, which refers to the concept of how adjacent layers in a networking models on the same computer work together. In this example that is shown here, The higher layer protocol HTTP wants error recovery, so it uses the next lower layer protocol TCP to perform the service of error recovery. The lower layer provides a service to the layer above it. So it is simple as like the HTTP or the application layer want to send some data between two hosts, and hosts means a computer, mobile phone, any device that uses TCP IP. So to be sure that all the data are received successfully, the application layer requests a service from the transport layer, and one of these services are the error recovery that is accomplished by the protocol that works at the transport layer, which is called TCP, or Transmission Control Protocol. Also, the figure shows an example of a similar function called same layer interaction. And when a particular layer on one computer wants to communicate with the same layer on another computer, this is called same layer interaction. What this means? It means that if we have a computer here and a computer here, and these are the TCP IP layers, application, transport, network, data link, physical, and same here. When we saw that the transport, here is Bob by the way, and here is Larry. When we saw that the transport layer at Bob computer sending to Larry, telling him please send me the lost or the missing part of the website content with sequence number 2, and then the transport layer replied with this part, this is called same layer interaction. So same layer interaction occurs between two different computers. But when the application layer here requested a service from the transport layer here, this is called adjacent layer interaction. So as a definition, or as more details of the how adjacent layer interaction that happens on the same computer and the same layer interaction on different computers, let's give some description about it. So the adjacent layer interaction on the same computer, on a single computer, one lower layer provides a service to the layer above it. As we saw, the transport layer, the transport layer, yes, provides a service to the application layer. So the software or hardware that implements the higher layer requests that the next lower layer perform the needed function. This is called adjacent layer interaction that happens on the same computer that uses the TCP IP networking model. Another concept called same layer interaction on different computers. The two computers use a protocol to communicate with the same layer on another computer, as we saw TCP. The protocol defines a header that communicates with each computer wants to do. This is called same layer interaction that is happened between two different computers. Now let's discuss the third layer that is called TCP IP network layer with number 3. Actually, the TCP network layer includes a small number of protocols, but only one major protocol, the Internet protocol, that the name here came from. We saw TCP from the transport layer and IP from the network layer. This is the most important protocol that works at the network layer. In fact, the name TCP/IP is simply the names of the two most common protocols, TCP and IP separated by slash. IP provides several features, most importantly, addressing and routing. And we will know exactly what addressing and routing means because it is a very important topic and it has a lot of things to be discussed, and other chapters will be focused only about addressing and routing of the network layer at the TCP/IP networking model. Let's go back to the example of the post office when Muhammad was trying to send a mail to Jasmine, and we will see how the addressing and routing works with the post office and how the routing will be accomplished on the computer networking. Here Muhammad has a letter that is destined to Jasmine in Berlin, Germany. Muhammad lives in Cairo, Egypt, and Jasmine lives in Berlin, Germany. So the post office man will come and take the letter or the envelope and deliver it to the local post office. Once the local post office will receive the letter, it will do the routing process, which is based on the destination address on the letter. And once it decides that, once it finds out that the destination is in another country, it will send the letter to the gateway inside Egypt that is responsible for sending letters outside the country. Now the gateway will send, by the way, the local post office will send through a truck to the gateway inside Egypt, and then Egypt will decide that it will send to the gateway in Germany via a plane. And as you saw, Cairo post office didn't decide to send neither to Giza or Alex post offices because they are not responsible for delivering a message to a different country. So it decided to send to the gateway inside Egypt, and then Egypt gateway decided to send to Germany post office gateway. This is called routing. So when Germany gateway post office received the letter, it will decide based on the destination address on the letter that this letter should be delivered to Berlin post office, the city where Jasmine is living, not in Cologne or Frankfurt. And it will use a truck to deliver as a medium to deliver the letter from the, let's say, the gateway to Berlin, whether it is in Berlin or not. Once the letter is delivered to Berlin, the post office man will take the letter and deliver it based on the address on the letter to Jasmine. This is how the routing inside the postal service. Let's go to the internet protocol and the postal service. We see the similarities between the two concepts. The TCP application and transport layers act like the person sending letters, Muhammad in this case, through the postal service. So the application and transport layers acts like Muhammad. These upper layers work the same way regardless of whether the endpoint host computers are on the same LAN or separated by the entire internet. It doesn't matter for these two layers whether the destination is near or far. They process the data similarly. Not similarly, but in the same way. So to send a message, these upper layers ask the lower layer or the layer below them, the network layer, to deliver the message. Then the lower layers of the TCP IP model act more like the postal service to deliver those messages to the correct destination. What this means? It means that the data link layer and the physical layer acts as the post office man, the truck, and the plane, and the post office itself. So to do so, these low layers must understand the underlying physical network because they must choose how to best deliver the data from one host to another. In case of sending from Muhammad's location to the gateway, it used two mediums or two different options. The first option was the post office man, as we saw here, and then the truck. This is how the data link and the physical layer works in the TCP IP networking model, but we are focused here about the network layer that do the routing process. So the network layer of the TCP IP networking model primarily defined by the internet protocol works much like the postal service. IP defines that each host computer should have a different and unique IP address. Actually, a different, not unique, because there are two versions of IP version 4 and IP version 6, and in some cases with IP version 4 you can have two same addresses in different LANs or different locations, not LANs, in different locations, called private IP addresses, but we will not deep dive in the details. All what you have to understand here is that IP defines that each computer should have a different IP address, just as the postal service defines addressing that allows unique addresses for each house, apartment, and business. Yes, the address should be different and unique outside the house in this example. Similarly, IP defines the process of routing. So here defines the addresses, the unique addresses. Here defines the routing so that devices called routers, and we will know exactly what are routers, can work like the post office to route or to route the letters or to forward the letters. But in this case, forwarding packets of data so that they are delivered to the correct destinations. Just as the postal service created the necessary infrastructure to deliver letters, post offices, sorting machines, trucks, planes, and personnel, the network layer defines the details of how a network infrastructure should be created so that the network can deliver data to all computers in the network. What this means, make an equivalent of the post office example on the networking example. Each layer defines a specific functions. So the Internet Protocol defines addresses for several important reasons. First, each device that uses TCP, each TCP IP host, and by the way, we call any device connected to the Internet as a host. This can be a PC, laptop, mobile phone, IP phone, and so on. Each device that uses TCP needs a unique address so that it can be identified in the network, and there are no conflict will exist. So IB defines how to group addresses together, just like the postal system groups. Just like the postal system groups addresses based on postal codes, like zip codes in the United States. So in this example, we will show you how routers will route packets from Larry to Bob, and we will show you how that is equivalent to the post office example. When Larry is trying to send a packet to Bob, it will send to the nearest router or the default gateway R1. R1 has two options, either send to R2 or sending to R3. Based on the routing function that the router do, it will determine that the shortest path should go or the best path should go to R2. Then R2 has two options, either send out of this interface or out of this interface. But because of or based on the routing process that the R2 do, it will determine to send the packet out of this interface that goes to Bob. This process is called routing. But there is another thing called addressing, where each device has something called an IP address. As you see here, Larry has 1.1.1.1 and Bob has 2.2.2.2, and this address is represented in the dotted decimal format. It's called dotted decimal format. And it has 4 octets. And each octet can has a number. So, as you see here, Larry has 1.1.1.1 and Bob has 2.2.2.2, and they want to communicate to each other, and each one has a unique address. The first thing we explained was the routing, and now we explained the addressing of the IP protocol. Actually, this slide repeats what I have said. So let's go to this slide. To define routers that are used by the Internet protocol. So what are routers? Routers are networking devices that connect parts of the TCP IP network together for the purpose of routing. Routing, we can replace it with forwarding. They are the same thing, routing or forwarding. So for the purpose of routing IP packets to the correct destination. So routers do the equivalent of the work done by the post office site. They receive IP packets on various physical interfaces, make decisions based on the IP address included with the packet, and then physically forward the packet out some other network interface. As we saw, R1, R2, and R2, 1, 3, they were connected like that. Each router 1 decided out of this interface, and router 2 decided out of this interface. Even router 1 has another interface, but it didn't prefer that interface because this one is better to send to R2, because if you will go through R3, you will take a longer path. This process is accomplished by something called a routing protocol that works inside the router, but we will not deep dive in that details because it has a specific chapter made for it. So let's discuss the IP routing basics, which we talk a little bit about it. Any device with an IP address can connect to the TCP IP network and send packets. As long as you have an IP address, now you are able to connect and send the traffic or packets. The TCP IP network layer using the IP protocol provides a service of forwarding IP packets from one device to another. This is the purpose or the function of the TCP IP network layer. And as we mentioned, the term IP host refers to any device that has an IP address and connects to any TCP IP network. This host can be a PC, can be a laptop, can be a mobile phone, can be an IP phone, and so on. Here also, we discussed the routing basics, the IP routing basics, when Larry server decided to send as a step one, when it needs to communicate with Bob on a different network, it decides to send to R1. Then, when R1 will receive the packet, it checks the destination that exists inside the IP header. Because as we mentioned, each layer uses some information stored inside the header. So in this case, we are discussing the network layer. There is a source IP and destination IP. And when R1 receives that packet, it will check the destination IP address and then forward out of this interface as a step 2, and R2 will do the same process, check the destination, and decides to send on this link to Bob. Now the data received from Larry to Bob in a process called routing. The TCP IP models, and actually now we finished the network layer. In this slide, we will discuss the data link and physical layers. So the TCP IP models data link and physical layers define the protocols and hardware required to deliver the data across some physical network. As you saw in the example of the post office, we described the post office man, the truck, and plane. Those are the equivalent of the function of the data link and physical layers, because it defines protocols and hardware required to deliver data across some physical network. Actually, the two layers work together quite closely. The physical layer defines the cabling and energy. For example, electrical signal if you are using copper wire, light signal if you are using fiber optic cables, and electromagnetic wave signals in case of wireless communication. So the physical layer defines the cabling and energy that flew over the cable or the air as a medium. The TCP IP data link layer provides services to the layer above it in the model. As we mentioned with the TCP, was the transport layer provides a service. Let's draw the model here, the TCP IP networking model. Transport layer provides a service to the application layer. The network layer provides a service to the transport layer. The data link provides a service to the network layer, and those works together, the physical layer and the data link layer. So when a host's or router's IP process chooses to send an IP packet to another router or host, that host or router then uses the link layer details to send that packet to the next host or router. If we have a router here and a router here, and there is a medium between them, the process goes to adding some layers, some headers and trailers to the data that comes from the upper layer or the above layer, and it uses the link layer details to send that packet to the next hop, router or host. For more details about this, as you can see here, the IP packet came from the network layer, goes to the lower layer, and the data link layer adds something called Ethernet trailer and Ethernet header. And this information describes the details of the link between the two hosts. And when the frame, we call this frame, and we will discuss it in the coming slides, the names of each part of each layer. When this frame is sent to R1, it do something called de-encapsulation, the opposite of the encapsulation. Encapsulation means to add a header and trailer or trailer, and the de-encapsulation process means to remove the Ethernet header, the header and or trailer. Because if the IP packet, the de-encapsulation process between the network layer and the transport layer, this will be, let's remove this one. If this is the IP packet or the data, and this is the IP header, when it goes to the above layer, it does de-encapsulation and removes that header. So in case between the data link layer and the network layer, the de-encapsulation removes the header and trailer, and between the network layer and the transport layer, it removes the network header. So encapsulation here means adding header and or trailer, and de-encapsulation means removing the header and or trailer. And these steps describes exactly what happens in the previous slide. The first two steps occur on Larry, and the last two steps occur on router R1 as follows. Larry encapsulates means adds header and trailer, Ethernet header and Ethernet trailer, creating something called Ethernet frame. Then Larry physically transmits the bits of this Ethernet frame using electricity flowing over the Ethernet cabling. The second two steps, router 1 receives the electrical signal over a cable and recreates something like regeneration, the same bits, by interpreting the meaning of the electrical signals. Once it regenerates, it does the de-encapsulation. Router 1 de-encapsulates the IP packet from the Ethernet frame by removing and discarding the Ethernet header and trailer. So, in the sending host, this is router and this is Larry, PC or router or laptop. On the sending host, it do something called encapsulation, and on the receiving host, it do something called Encapsulation. Encapsulation means adding headers and or trailers. Encapsulation means removing headers and or trailers. As a note here, headers exist at the beginning of the message and trailers exist at the end of the message. If this is the sending host, then and it sends in this direction, this is the header and this is the trailer. Each has contents that provides a specific service for the layer above it. The data link and physical layers include a large number of protocols and standards. For example, the link layer includes all the variations of Ethernet protocols and wireless LAN protocols. So, the link layer has details about the wired LAN or wired Ethernet LAN and wireless LAN protocols. In short, the TCP IP physical and data link layers include two distinct functions, respectively. Functions related to the physical transmission of data that belongs to the physical layer, plus the protocols and rules that control the use of the physical medium, the data link layer. So this is the function of the physical layer, and this is the function of the data link layer. As you can see, the explanations of how HTTP, TCP, IP, and Ethernet do their jobs when sending data. Each layer adds its own header, and some other layers adds a header and trailer like the data link protocols. So the term encapsulation refers to the process of putting headers or inserting or adding headers and sometimes trailers in case of the data link layer around some data. And the de-encapsulation process means to remove that header and or trailer. So in this slide, we are going to discuss the data encapsulation terminology and its names. The application layer here is responsible for the data. It delivers the data to the transport layer in case of encapsulation. In case of the sending host, this is the sending host. When the transport layer receives the data from the above layer, it adds TCP header, and all of this is called segment. When the network layer receives the stream of data from the transport layer, it considers the TCP and data as data. All these are considered as data for the transport layer, for the network layer, and adds its own IP header, and all of this is called packet. And when the data link layer receives the data from the network layer, it considers, by the way, the data and TCP and IP as data. It doesn't know anything about the details here. It adds a header, data link header, and data link trailer, and all this is called frame. And then send to the medium as binary stream or bits. So those are the 5 steps of the data encapsulation. Here the names of the TCP/IP messages that we mentioned in the previous slide. The data plus the TCP or UDP header are called layer 4 segment. The data and the IP header are called layer 3 packet. The data and the link header and link trailer are called frame, layer 2 frame. Here in this slide, we are going to discuss the differences between, or more details between, the OSI networking model and the TCP/IP, some comparison in the names. Actually, even the world uses TCP/IP today rather than OSI. We tend to use the numbering from the OSI layer because the OSI layer has more layer numbers and more details than the TCP/IP. So, for instance, when referring to an application layer protocol in a TCP/IP network, the world still refers to that protocol as layer 7 protocol, even if it is inside the TCP/IP, because TCP/IP is used actually and in the network. But when we call the layers, we use the numbering used by the OSI reference model. We don't call layer 5 or application layer. We call it application layer in TCP/IP, but we call it layer number 7. These 4 layers are the same: the physical, data link, network, transport. But the application layer at the TCP/IP are detailed to application, presentation, session at the OSI reference model. That's why we call it reference model, because we use these numbers. For application layer, we call layer 7. For transport layer, we call layer 4. For the network, layer 3. For the data link, layer 2. And physical, layer 1. Last thing here is the OSI data encapsulation terminology. As we saw with the TCP/IP in this slide, the data encapsulation terminology with TCP/IP, we have data encapsulation terminology for the OSI reference model. Actually, they are almost the same. Just the data comes from the application with some layer 7 header and goes to the lower layer as data and add layer 6 header, goes to the lower layer as data, which is the session layer here, and adds layer 5 header. Each layer adds its own layer, its own header, and so on. So this one is called layer 7 protocol data unit, and this data is called layer 6 protocol data unit, data plus layer 6 header, and so on, till the data link layer with the layer 2 trailer and layer 2 header is called layer 2 protocol data unit. So till here we come to the end of this presentation. I hope it's been informative, and thanks for watching.